Well, let's consider now an object sitting at rest on a table. Okay, so we have a table, we have an object sitting on the table, some mass m. Okay, now we know that gravity is exerting a force on it, but it's not falling because it's sitting on the table. And so there has to be some upward force on it. Okay, and that upward force balances against it falling. Well, it's pretty clear that this upward force is equal to mg in this example right here. Okay, same for you. So you're sitting, you got a chair, and you sit in a chair. Okay. And so there's a downward force mg on you. The chair exerts an upward force mg on you to keep you from like just falling and going splat. Of course, I'm clumsy enough I can fall and go splat from a chair, but that's just me. Okay. So now what happens though if your object is on an incline? Now what happens is gravity exerts a force like this. Okay. And so what does that mean? Well, obviously it can't go straight down because the incline's in the way. So we know what's going to happen. It's going to try to go sliding down the incline. Okay, we're ignoring friction. Friction comes next chapter. For right now, we're ignoring friction. So it slides down the incline, but it can't do that because the force is straight down. So how does this work? Well, think about it at the subatomic level. This thing is made up of atoms. The surface is made up of atoms. The outer parts of the atoms are all electrons that repel each other. And so there's actually a repulsion between the two. And so this repulsive force, that's why you set something at a table, it doesn't go falling through the table because the atoms of the table repel and force upwards. Here they also force, but they're going to force straight this way. And so what happens is if I put my x-axis like this, my y-axis like that, and I can do it any way I want, but I put my x and y-axis like that, then that means, now why would I do something weird like have a tilted x and y-axis? Because now it's moving in one dimension. Okay, it's just going to go down the incline. And so you know from chapter 4 that one-dimensional motion is easier than two or three-dimensional motion. So I want to tilt my axes to make it one-dimensional. Well, that means that this force, this repulsive force, the weight is going to have two components, an x and a y component. So this repulsive force only balances that component right there. Okay, and so it's going to be equal to, well, now we got to figure this out. So this is a right angle right there. This is theta. Okay, so that means that right angle right here. So this is going to be theta right there. So that means that this component right here is going to be mg cosine theta. So this up here has to be mg cosine theta. Just for completeness sake, this is mg sine theta. Okay. And so that means this force balances there. So the force is always perpendicular to the surface. And so it's always perpendicular to the surface. So we want to call it something. Well, in math, they have a term for perpendicular. It's perpendicular. But they have another term for perpendicular because one word meaning this is not quite sufficient. So they have another term for perpendicular, and that is orthogonal. Well, they actually have another word for perpendicular, and that is normal. So we call this the normal force. That mainly just means it's perpendicular to the surface. So we got here this incline, and so we've got mg pulling down, okay, and we have a normal force pushing like this, so I'll call it F sub n for normal force. We know the normal force is mg cosine theta, but what about this right here? That component right there is mg sine theta. So that means that if you draw a free body diagram for this thing, we've got mg pulling down, we've got normal force like that, so these two add together to make this mg sine theta, so that means we got mg sine theta as an unbalanced force. There's a force pulling down, there's no force pulling back, and so that means it's going to accelerate ma. These cancel, and so we're going to say the acceleration down the incline is g sine theta. Okay, so now we can figure out how quickly something accelerates down an incline. Okay, but the main point of this lecture was the normal force itself. Okay, so we'll get back to the going down the incline in a bit. So the normal force, okay, and so I want to figure out what is the normal force here. And so the normal force, though, is not always just what it looks like it is. For example, here we know that we get mg pushing down. What if I'm pushing down on it with some applied force? So let's say that this object has a mass of 10 kilograms. So that means that mg is 981 newtons, okay, and 98.1 newtons is 98.1 newtons. So it's 9. So what if this applied force is going to be 20 newtons? So I want to know what's the normal force. Well, the normal force is, well, you look at it. So the normal force has to balance all the other forces. So the normal force would be equal to 118.1 newtons. Okay, now students often make a mistake thinking the normal is just mg, or on an incline, okay, on an incline we just calculated here. We got mg, okay, and we've got the normal, and so you just assume F normal equals mg cosine theta. That's not true if there's another force pulling on it. The normal is only whatever it needs to be so that the acceleration in or out of the plane is 0. The normal is not a set number. The normal is whatever it is required for that condition, for the acceleration perpendicular to the surface to be 0. Okay, so do not think that the normal is always mg or only mg cosine theta. The normal is whatever it needs to be.